Hey guys, coming at you today with the last video before we take our test tomorrow. I want to review one more time. It's just an area that a lot of people struggle with. Justifying continuity at a point, as well as justifying problems using the intermediate value theorem. And then I also want to take a look at just a quick table problem before we go. Again, it's really, really important for these we're going to start with the continuity problems. It's really important that you justify these using the correct notation. Okay, notation is super, super important. Also, just for any time I ask you about continuity at a point, it's really important to remember the 3 steps. Okay, these 3 steps need to be memorized from now until you're done taking the AP exam in May. So here are the 3 things that need to happen. Okay, I'll go back a slide here real quick. Okay, so f is continuous at x equals a. So it could be, in the problem it might be at 2 or 5 or 7. But just in general, at some point x equals a, if and only if the 3 things are present. All 3 things have to be present. If I fail any of these 3 steps, f is discontinuous. Okay, and we'll think about what kind of discontinuity it would be. Okay. So step 1 for proving continuity at a point, the limit must exist. Okay. So we're going to have to show that the limit exists. If I give you a piecewise function that splits at a number, like in the problem you'll see coming up, the piecewise splits at 2, right? So there's a different function for x less than 2 than there is for x greater than or equal to 2. To prove that the limit exists there, you're going to have to show left and right hand notation. Okay? So you may need to show left hand, right hand limit notation. Again, for limit as x goes to a of f of x to exist, limit as x goes to a plus the right-hand limit at a must equal the left-hand limit at a. Okay. That's step 1. If the limit doesn't exist, like if you get 2 different answers for your right-hand and your left-hand limit, let's say you get 10 and 15, then we know we have a jump discontinuity. If you're getting infinity or negative infinity for your right hand and left hand limits, then we're going to have discontinuity due to a vertical asymptote. But if the limit exists, that's just step 1 in proving continuity. Doesn't mean that the function is continuous. It just means it passes step 1. Step 2, f of a must be defined. So the function must be defined at that point. If the function is undefined at a, then the function is not continuous. And then step 3, f of a must equal the limit as x goes to a of f of x. We need to know those 3 steps, and we need to be comfortable using the notation for those steps. So let's apply that knowledge to this question right here. Okay, so here we have f of x is a piecewise function. We follow the formula x squared plus 4 for whenever x is less than 2. We follow the formula 3x plus 2 whenever x is greater than or equal to 2. Okay, so the question is f of x continuous at x equals 2? Justify your answer. If discontinuous, state the type of discontinuity. Okay, so I need to go through my 3-step process. The first thing I have to do is find the limit as x goes to 2. For f to be continuous at 2, the limit as x goes to 2 must exist. Because I have a different function for the left side of 2 than I do for the right side of 2, I need to show my left-hand, right-hand notation. Okay, it's very important tomorrow when you get this type of question that your notation is on point. I usually label my justifications with a 1, 2, 3 steps. So the first thing I'm going to do here is I'm going to do the left-hand limit as x goes to 2. I show it's a left-hand limit by putting the little superscript minus up there. So to check the left-hand limit of f at 2, I need to use the x less than 2. I need to use the top function there. Right? That's going to be approaching 2 from the left side, like 1.9, 1.99, things like that. Okay, so I'm going to plug 2 into my top equation there, and I'm going to get 2 squared plus 4. 2 squared plus 4 equals 4 plus 4, which is 8. Okay, so the left-hand limit at 2 is 8. I need to now check the right-hand limit at 2. Again, if you do not put this notation here, right-hand, left-hand limit, you won't get credit for this. So be sure to practice it. Be sure you're ready to demonstrate that tomorrow. My right-hand limit, I'm going to use this bottom function here because that's where x is greater than or equal to 2. So I'm going to do 3 times 2 plus 2, which is 6 plus 2, which is 8. What I'm finding here is that my left-hand limit and my right-hand limit are equal to each other. Okay? Now we know that that means the limit must exist, and the limit as x goes to 2 of f of x equals 8. You need to state that. So sometimes people just move on to step 2. We're not done. We write, therefore, limit x goes to 2 of f of x equals 8. You need this step as well. Okay? So that shows us we're done with step 1. We proved that the limit exists as x goes to 2. We found that it exists and it equals 8. Now I move to step 2. I need to figure out what f of 2 is. I need to know if my function is actually defined at 2. Well, when I look up at my piecewise function again, I see that 2 is actually included in the bottom function. 2 is not included in the top function. By the way, if the bottom function was just x greater than 2, it didn't have the or equals to in there, then f of 2 would be undefined, right? We don't plug in anything for 2. So f of 2, I plug it into the bottom. I get 3 times 2 plus 2 again. To get 8. So that passes step 2. Now I'm not done yet. Step 3 then, I need to show that f of 2 and the limit as x goes to 2 of f of x are the same. Are they? Well, yeah, I got 8 for both of them, right? My limit gave me 8. F of 2 gave me 8. Therefore, step 3, I can say f of 2 equals the limit x goes to 2 of f of x. And then I can say equals 8, just to show that I calculated that. Okay. This right here passed all 3 steps to prove continuity. So I'm just going to take one more step. Don't forget this step. Sometimes people put all 3 on there, but then they never answer the question. The question is f continuous at x equals 2? Yes. Therefore, f is continuous. Don't just say f is continuous. Tell me at what point. At x equals 2. Done. Okay? Notice I didn't write a lot of words, but I have a lot of notation here. Okay? The notation is really, really key here. The words are just therefore, and f is continuous at x equals 2. Okay? The second piecewise here. I want to know continuity at x equals 1, because 1 is the place where my piecewise changes, right? I use 3x cubed minus 5 for all values x less than 1. I use 7x minus 9 for all values x greater than 1. And I use negative 6 at x equals 1. Okay. So I want to prove continuity, so I have to go through my three steps. Step one, I need to figure out the limit as x goes to 1. Well, because I have a piecewise that splits at 1, I need to check a left-hand limit at 1 and a right-hand limit at 1. I say the limit as x goes to 1 minus of f of x equals, and again, think, which function am I going to plug into for the left-hand limit? Well, I have to plug it in. I'm approaching 1 from the left side, from the more negative side, so I need the less than, the top function. So it'll be 3 times 1 cubed minus 5. 1 cubed is 1, 3 times 1 is 3, 3 minus 5 is negative 2. Okay. Now I need to check the right-hand limit. Well, that's going to be x greater than 1. So I'm going to plug it into 7x minus 9. So I'm going to plug 1 in for x. 7 minus 9 is negative 2. Since my left-hand and right-hand limits are the same here, I know that the limit exists. But I need to state that. Therefore, the limit as x goes to 1 of f of x equals negative 2. So the limit exists, it equals negative 2. Step 2, the function must be defined at 1. Okay, so I need to check f of 1. I don't plug into the top or the bottom because neither one includes 1. I have to use the middle function there. When x equals 1, it says f of x equals negative 6. So f of 1 equals negative 6. Again, I checked number 1. I checked number 2. Well, what happens at step 3? My function is defined, my limit exists, but the two things are not equal to each other. So I'm going to say f of 1 does not equal the limit as x goes to 1 of f of x. Okay? Therefore, f is discontinuous at x equals 1. Okay? Now it says, if discontinuous, state the type of discontinuity. Well, what I have here is a limit existing. The limit equals negative 2, but at 1. But f of 1 is negative 6. I have something like this. You think about it in a graph. I have a limit equaling negative 2, but I have the function defined down here at negative 6. If we pass step 1, but fail either step 2 or step 3, then we know that our type of discontinuity is a removable discontinuity. Okay, so I know it's a removable discontinuity. If you get that ahead of time, you can just wrap that into your, therefore f has a removable discontinuity at x equals 1. It's kind of a nice way to say that too. Okay, let's take a look at the last one. Part 3. So it says, for what value k is f of x a continuous function at x equals 5? So now I'm figuring out, okay, what could k be? So f is continuous at x equals 5. Well, for f to be continuous at x equals 5, first off, the limit must exist. Now, this piecewise doesn't have a different function for x less than 5 or x greater than 5. It just has a function for x doesn't equal 5. Okay? So that top function, x squared minus 25 over x minus 5, that's going to be both our left side and our right side. So I don't have to do a left-hand, right-hand limit here. I just have to do the limit as x goes to 5 first off to figure out what that is. So step 1, right? The limit must exist. I don't have to do a right-hand, left-hand because this top function right here works for numbers a little bit less than 5 and the numbers a little bit greater than 5. Okay? So the limit as x goes to 5 of f of x, right? I'm just going to plug 5 into my function. What I get is 5 squared minus 25 over 5 minus 5. Well, that gives me 0 over 0. So that's a whole. Okay, but we know that limits exist at wholes. So I have to think about what can I do with this x squared minus 25 over x minus 5? How can I simplify this to actually calculate what the limit is? Well, hopefully you see that top factors, right? So this is the same as limit x goes to 5 of f of x, right? I'm going to have x plus 5 on top, x minus 5, over x minus 5. So what I can do now is cancel out my x minus 5s, which is giving me my problem. And now when I plug in 5, I get 5 plus 5 equals 10. So I know the limit as x goes to 5 is 10. So I know the limit exists. The function is defined, right? F of 5 is said to be k. But they want to know what should I choose for k to make this thing continuous? Well, f of 5 must equal the limit as x goes to 5, which we already know is 10. So f of 5 must equal 10. This must be true for f to be continuous. Therefore, k must equal 10. IVT. Okay, for our intermediate value theorem, let's go to the next page. Okay, so here we have a table of values, right? And it says RT is the rate of fuel consumption in gallons per hour with 0 is less than or equal to t less than or equal to 18 hours. Selected values are given in the table above. Here's the most important part. R of t is a continuous function. One of the problems on review sheet 2, I never told you that our function was continuous, so we couldn't use the IVT. But now that once you know R of t is continuous, then we know that the IVT is in play. Okay? So it says explain why there is a times c where 0 is less than c is less than 6, such that R of c equals 25 gallons per hour. So they're giving me a window here, 0 to 6, right? Between 0 and 6 on this table. So c is going to be somewhere between these two numbers. I want to know, is there an R of c equal to 25? Well, just thinking about this, I'm thinking, okay, to go from 22 to 46, do I have to go through 25? Well, the answer is yes, as long as the function is continuous, and the function is continuous. So I'm going to prove this using the IVT, the intermediate value theorem. So here's what we need in terms of an explanation here. So I need to mention 3 things. I need to tell the grader that R is a continuous function. I need to state the surrounding values of R of 0 and R of 6. And then I just need to invoke the IVT. So here's what I got to say. 6, R of t is a continuous function. And I know R of 0 is 22, and R of 6 is 46. Right? I'm stating that 25 is intermediate to 22 and 46, right? It's in between those numbers. There must be a C. A times C. Now I'm just kind of like copying this phrase right here. There must be a times C where 0 is less than C is less than 6, such that R of C equals 25 because of the IVT. rows of. Okay. So again, when I'm grading this, here's what I'm going to be looking for. Number one, does your sentence make sense? Number two, did you mention that RFT is continuous? I did. Check. Did I state the surrounding values? I did. Check. Did I mention the IVT? I did. Check. I'm going to be looking really hard for those three things. If I don't see, if one of those three things is missing or more, it's not going to get credit. Okay. The last question I had was about doing limits from tables. Let me just give you an example of that real quick. I'll just make one up. This isn't out of our review sheet. Eight, 2.98, 2.99, 3, 3.01, 3.02. Okay. So if you see a table like this, okay, I might say that F has a removable discontinuity at x equals 3. The question is, that I'm going to ask is, what does it appear the limit as x goes to 3 of f of x is? Okay. Now remember, limits are about, as we approach an x value, what y value are we approaching? It does not care what's happening at 3. So the fact that f of 3 equals 10 is not part of this problem. Okay? The limit as x goes to 3 here is, as I get closer and closer to 3 from both sides, what y value do I keep getting, what f of x value, y value do I keep getting closer and closer to? Well, it appears from the left side I'm approaching -4. It appears from the right side I'm also approaching -4. So I'm going to say that my limit as x goes to 3 of f of x equals -4. The only answer that would be 10 is, what is f of 3? F of 3 equals 10. But not the limit. The limit cares about what's happening around it. Okay, that's it for tonight, guys. Study hard. Work on your justifications. And I will see you guys tomorrow for the test. You'll do great. Talk to you later. Bye.